Right, so welcome everyone to the last talk of the DG seminar. So first of all, I'd like to begin by thanking all the speakers who gave talks and all the participants and everyone who was like part of this whole thing. And yeah, so in the last talk, basically we'll kind of see like why we did all whatever we did in the seminar and how we're gonna prove the result that is theorem 4.2.1 in Stefanich paper, I guess. So, right, so that's the point, and the talk will probably be less than 90 minutes, but or maybe more, but we'll see how that goes. So let's start with some historical context. I'll just recall what the classical Tanaka duality is. So you start off with an affine group scheme G over K, then GK is equivalent to odd. So these automorphisms like this, right? And then the geometric formulation is that the heart of rep G is equivalent to the heart of UKVG. Right? So what is the question? The question that we care about is, can we recover BG from UKVG heart? Right. Okay. Right. So Lurie proves an SAG. So I don't remember exact numbers of X, quasi geometric stack, and Y a QCGS spectral algebraic space. With yeah, then you have Q call X and Q call Y. Right? So this is like basically this is like the infinity category of symmetric monodal functions from Q call X to Q call Y. Like just recalling everything from Q call X to Q call Y. Right, so it's like maps from Y to X is mapped to per star. Right. With image characterized by tameness conditions. So what are those? Number one, that F. Yeah, F preserves flat objects and exact sequences. Number two is that F is so we'll actually see a proper form later in the talk. F is connective plus the right adjoint of F that I think Lurie calls G, preserves colors plus projection formula. We'll actually see this spectral. So right, so what is Stefanich proof and what that we've been trying to chase throughout the seminar? So this is like theorem 4.2.1 in Stefanich's paper. So X and Y are geometric stacks. Suppose X is quasi-compact with quasi-affine diagonal. Then the pullback functor induces an equivalence this is the statement that we actually approve. Subscript C alg. Yeah, PRL Q co X All right. So yeah, so let's see what are the improvements that this like statement has for us. So improvement in terms of like removing the tameness hypothesis. Like the first is like there are like no tameness. So this is like the one that we care about, no tameness conditions on the functor. All right. And the second one, oh yeah, right. So Y is an arbitrary geometric stack, right? So it's not just spectral spec space. And so this like works with connective parts and so on. Like the and yeah, you can also say that it only requires like the quasi-affine diagonal, not an affine diagonal. Right? So Stefanich actually gives us a couple of proofs. So we'll see both of them actually. So the first proof is uh, so it's an application of, so we'll see everything in detail. Lurie's theorem plus the admissibility of Q cos Cn, right? And then the second proof is that, so for the second proof is that use the affineness theorem for sheaves of categories. Right. So let's see our first proof. First proof, right? So lemma. Okay. So by the way, I'll be referencing this theorem. Like I'll call this theorem 4.2.1 throughout this talk. So okay. So lemma is that like both sides of theorem 4.2.1 are limit preserving in Y. Right. So I'll give you proof sketch. So for YX, so for this like the stacks, okay, I'll just write it down. Stacks form and infinity tuples, right? And so this mapping space is a sheaf, right? And now for the other side, CLHPRL. Yeah, okay. Okay, so first let's write Y to be limit YI. So this is like, so it's like it's like a limit of affine schemes, right? Then Q cos Cn is similar. Sorry, it's equivalent to Cn and CAlge growth comp. Right. Now, since right, this sub CAlge PRL Q coax Cn dash sense limits to limits, we get CAlge Q coax Q co Cn. This is just limit of this Q co X even and Q co YIs. Okay. So right. So corollary, and let's call this corollary star because I'll actually reference this later. So to prove, so the corollary is that to prove theorem 4.2.1 for all y, this is just for bookkeeping purposes. It suffices to prove it for equals to spec r. Right. So fine. Okay. So right. So now let's revisit Lowry's theorem. Say G.
Yeah, I'm sorry. Can you have a
Yeah,
question?
yeah,
If you
sure.
scroll up a little bit, do we need that our limit, that the thing we are pressing Y off is one of those flat covers? Because the like limits in Grothendieck categories are only computed in PRL when the transition maps were these
Yeah.
were not compact, but the other thing.
Hmm.
Well, wasn't there a statement of this kind?
Think so as
I
well.
thought like limits in Grothendieck categories don't always agree with the limits in PRL, right?
Hmm. I don't know. Let's see. So you're saying that there should be like some additional conditions?
I think that it's
Yeah,
what's
usually you need that the transition maps are legs, right?
right that you're right, Lex was the word I'm
Ah,
looking for, right? But I mean
okay.
this can always this is always arranged in the cases we care for.
Right,
Because
right.
if
So
this is
so you're
just if
saying
you
that,
take
yeah, yeah, I
our
should
yeah.
mention that, right?
I don't know, I was just
Okay.
trying to clarify that in my head mostly.
Mm-hmm.
Okay.
Okay. Well, maybe we'll discuss about that later. Right. So yeah. So Lewis theorem. Right. So X is like a quasi-geometric stack. Y is QC QS space. Then pullback after gives a fully faithful embedding. Whose essential image consists of symmetric monoidal functors from Q co X, Q co Y that satisfy the one that F preserves colimits. So G is the right adjoint. So equivalently admits right adjoint G. F is right T exact. Equivalently, G is left T exact. G preserves small colimits and projection. Oh, right. Let's see. So yeah. So for F and Q coax and say okay, let's say G prime and Q co Y, the canonical map yeah, G of S as an equivalence. Right. So remark when Y is affine, condition to is automatic, for F restricted to QX Cn, and we only need to check the extension to Q call X satisfies to do 4. Right. Okay. So what is the strategy that we have? So given F from Q call X C to Q call Cn, so colimit preserving symmetric monoidal. Y is spec R. Like first you extend F to say F tilde from Q call X to Q call Y, right? Via left con extension. Then I guess yeah, verify that F tilde satisfies. So this 1 to 4 that we have like in Lewis theorem, right? And then basically conclude that F tilde is upper star for unique F from Y to X. Hence F is upper star. Right. Okay. Okay. Let's see now. So that is the strategy of the first proof. So construction. Define this F upper F tilde Q call X to Q call Y as the unique colimit preserving extension of F along the inclusion. Right. Lemma that F tilde is symmetric model. Okay, let's see. So since Q call X is generated under colimits by Q call X and the tensor product preserves colimits in each variable. The symmetric monoidal structure of F extends extends uniquely, right? So like so a bit more formally, if you put it, so the composition that is composition tensor. So yeah, so this extends to a colimit preserving functor. Right. And which factors through like f tilde tensor with f tilde factors through f tilde. Right. Okay. I will verify like these verification of 1 to 4. Like that is Lewis, the ones in Lewis theorem. Right. So first you start with like let f from q call Cn to q call Cn be given. Y is car. Right. So the condition, like first condition, is that right. So the first condition is that like f tilde should preserve colimits, which is like instruction, the way we've constructed it. Condition 2 is that tilde is right t exact. Right. So which is also evident as sense. Right. So for the condition 3, so here that's a bit of work. So we need to show that tilde has a colimit preserving right edge. Right. So let's call this a lemma as a colimit preserving right adjoint. So okay, first write f as a composition as follows. So go from q coex Cn to turn the q coex Cn q co y Cn mu q co y Cn, right? Where this e that we have. So let me write this where this e from Cn to Cn is the unit map, right? So that is basically induced by y to spec of s, right? And mu is the action map of the q coex Cn module structure, right? On this q co y Cn, induced by this f, right? Okay, let's see. So now apply P. So right. So then this is P F. So be P of mu. It's P of sorry. ID identity. So it's P of E. Okay. Now so step one is that since y is affine, SPE has a so it has a T exact colimit preserving right adjunct, right? So I guess so it is like the forgetful functor from Q call y to SP, right? Step 2. So let me write this: the forgetful functor Q call SP, right? Step 2 is right. So this is like This is theorem 3.1.1, I guess. Right, so X it states that X is so we'll actually use this. An X is quasi-compact geometric stack with diagonal of X. You see QS relative algebraic space. Then 1 Q coax Cn is an admissible algebra and GraphCom. And then if you assume that X has affine diagonal, then this Q co XCN and X R are almost rigid algebras. And GraphCom and I think PRL, right? Okay, and right, so we'll actually so this is like theorem 3.1.1, and there's another theorem that we'll be using. So that is theorem 2.4.3. So all these references, by the way, are from Stefanich's paper. So mathcal A is an admissible algebra in GraphCom, and mathcal M is a left mathcal A module in GraphCom. Then the action is compact, and the right adjoint to is right T exact up to the shift. Right. So we'll actually use these three. So this is like the step two. So remember, so this has been step one, and now so now using this theorem 3.1.1 follows that Q coaxial is visible, as you can see, right? And by 2.4.3, yeah, this theorem, it follows that mu has a whole limit preserving right adjoint, that is right T exact up to a shift. Okay, so that was step two. Step three is the composition of functors with co-limit preserving right adjoints has a co-limit preserving let's see, so the composition functors with the co-limit preserving right adjoints has a co-limit preserving right adjoint. So like this, the composition of the right adjoints, the reverse order, right? So this SPF has a co-limit preserving right adjoint, right? So that was condition three. Now comes condition four, that is the projection formula, right? Okay, so let's start with the lemma. So the right adjoint G of SP tilde satisfies, let's say, dash for f dash in q call x and g dash in q call y, so dash tensor which is equivalent to f f tilde f dash tensor to, yeah, right. Right, so okay, so let's see the proof sketch. It'll just be a proof sketch. So consider the following diagram and graph Stefanich-Tannak SPF equals Hugo Xian Cn SPF and SPF equals Cn then right and SPF identity of identity tensored with F. So this will be Cn tensored with go Y Cn equal like Cn equal and SPF mu Y SPF equal just need a minute. So, sorry about that. So where was I? Yeah. Okay. So I'm applying SPF UI to get Q and right. So let's consider this square and growth count. Now, right. So let's recall this. So this is like theorem 2.4.3. So we've seen this before, but recall. I'll just write it down. So A is an admissible algebra in graph comp. So let's first yeah, okay. Graph comp and M is like a left a module in graph comp. Then suppose f from M to N is a morphism of left A modules with F compact and the right adjoint to SPF right exact up to a shift, then the following square is vertically right adjointable. So the square is PF mu m identity this P of F is vertically right adjoint to right. Right. So using this, the above square. So the sorry about that. Let's see. Where was I? Okay. So it seems like I don't know. So it seems like I lost something else for some reason. Let's pretend that did not happen and let's get back. So okay, let me try and redo the whole square thing again. Oh, jeez. Here you go. And this was so I'll just write it down. So and for this you apply identity tensor F, and then here you'll get like this tensor to equalize, and here you're gonna apply mu y, and then this will be SPF of F. Right. So we saw this like theorem 2.4.3. So using the above square is vertically right adjointable as F is a morphism of Kirchhoff-Axial modules. Right. Now recall that. So I think this is remark 2. Recall that by remark 2.3.14 of Stefanich, vertical right adjointability is in graph ST comp means if um, if we denote by gx and gy the right adjoints of sp mu x and sp mu y, and say I don't know h, the right adjoint of sp identity tensor stuff, and the canonical two-cell gx goes with this is supposed to be a capital F times so this like R is like the right adjoint or is an iso, right? So now this says P of mu x corresponds to under stabilization to the action map Q car x. And similarly for like SP mu y, corresponds to this action map induced by like F tilde. And now like so instead of like going through all the details, I'll just say that unwinding this, unwinding all these definitions like the isomorphism of two cells will give us projection formula. Like honestly, I don't have time to explain the whole part. Right. So to conclude, so this basically concludes the first proof. Conclusion. So to conclude, so using the last two lemmas, this F tilde satisfies all conditions of Lurie's theorem. Therefore, there exists a unique f from y to x, such that F tilde is first term, and basically restricting to connective objects, we get that. Right. So this basically shows you that the function theorem 4.2.1 is essentially surjective for y affine, right? And then fully faithfulness follows from Lurie's theorem. Now, so remember we had this corollary star. So I think So corollary star was basically so I think it'll still be there. This one to prove so it suffices to check it for y affine. So therefore basically from this corollary star, it follows that the result extends to all geometric stacks y. So that concludes my first theorem's proof. Now, second proof via affineness. So this is for me the most interesting part. So let's see the affineness theorem. Okay, so you start with X quasi-compact with quasi-affine diagonal. Then there's like a thing called phi X mod U go XEN growth comp to Q comp PC comp X is an equivalence of symmetric monodal categories, right? Corollary is that so all these things we have, like if you have actually paid attention to the last few talks, like we've actually talked about these. So the corollary is this enhanced function, the enhanced sections thing. So this is so this goes from to Q car PST com X to mod Q cross com as an equivalence. Right. Right. So okay, so what is the strategy? So let's try to do that strategy of the second proof. So the first step would be to show that this Q call Cn this function is fully faithful from affine schemes to C-alg graph comp. Right. And then use the affineness theorem. So use the affineness theorem to relate maps y to x2 to commutative algebra objects under C. And then the last step is just to use descent to prove the correspondence as an equivalence. So this is like the kind of strategy of the proof here. Okay, let's move on. So consider the commutative diagram over X up This goes Q call CN C alg growth com mod. So we'll give this a name. So let's call this like something. So yeah, to CN C alg growth com, and let's call this Q. So here P is yeah, so P is basically this forgetful functor that from Z to X this maps to Z, and Q is the forgetful functor like Q C to say some C to Q call X C, and so this maps to C, of course. Okay, so now let's see another lemma, which we'll call star prime because we've already used star. So the bottom. So remember the square is like square times the bottom horizontal row in the square is fully faithful. So yeah, so this part actually I'll skip the proof of this part in the time constraints, right? So now we'll restrict to affine targets for that. Define the subcategory C alg growth comp subscript F um, uh, CN. So this is just F up times in C alg growth comp, of course. And then you have C alg growth comp mod Q call C. Right. So right. So for this category, the objects are like pairs. So I don't know. Let's say C and Q cox Cn to C. So let's call this phi. Right. Um, right, where the C is like equivalent to some Q call Z Cn or some affine Z. Right. That's what it means. So then lemma. Jeez. Okay. Okay, so the star that I had used was for the corollary. Okay, let's use a star for this lemma now. Sorry about the notation. The affineness equivalence basically induces this, C alg, this equivalence between C alg graph comp half mod Q cox Cn and C alg of 2Q cop PST complex F, right? So the right hand side, as you can see here, so the right hand side, this basically consists of commutative algebra objects and two Q-cop PST complex whose underlying sheaf is locally locally of the form Q-call ZCN. Right. Right. So this one will also be kind of a proof sketch. So for this, if I remember, okay, so apply C alg to this phi x from the affineness theorem, right? Uh, So we need to check this phi x preserves the property. So the property that let me write it like this: underlying category is Q call ZCN for affine Z. So this is the property. So now this actually this follows from the following lemma. Right. So suppose X is a quasi geometric stack with quasi-affine diagonal, let P from U to X be a morphism of geometric stacks. Suppose Z is an affine scheme and F from F Q cosine to QQ. ZCN is so it is a colimate preserving symmetric monoidal functor, colimate preserving symmetric monoidal functor. Then if P is affine, then skew call U CN to relative tensor because ZCN is Q call Z prime CN for some affine Z prime. So, right, so if C is like, so we use this lemma, if C is like Q call ZCN with Z affine, then for any map, so say eta from spec R to X, eta upper star phi inverse C is equivalent to so this mod CNR is a form Q call Z CN for some affine. Okay, so now let's define the functor. So this is like the comparison functor. So for me personally, I kind of find this notation. I don't really remember what this. I don't know what this Greek letter is called. So I think this is the notation Stefanich used. So I'll be using something that I remember. So psi, I guess, half x, something easier. So this goes from affine where x up to C alg of 2q co pst co x affine, right? So you define basically this by, so let's call this construction or a definition, whatever. So you define this, so you take a map from F to X, so this maps to F lower star, right? Okay, so lemma is that the square that we had is, so this square times is equivalent to this square. We'll prove how. Or maybe I'll just say it. Half x C alg count x half is p half up. So this just follows from by the definition. Yeah, it's pretty straightforward. It follows from the definition of like fiber product and this lemma star that we have here. Let's get this one here. Okay. Let's see. So now we want to prove that this psi half x is an equivalence, right? So let's start with the case one where x has affine diagonal lemma. If x has affine. So let's call this, I don't know, star 2. If x has affine diagonal, then this, so this is like psi f x is an equivalence, right? So for this, the idea is that, like, you write x as a colimit of a diagram of affine schemes. So say x sub alpha with transitions. I think this is what was kind of mentioned towards the beginning of the talk. For each alpha, consider this f x alpha, x sub alpha. So this is like a map from f over x alpha up to c alge to q cap pst com x alpha f. And now using this lemma star prime, that was, if you remember, this one, so that this row is like fully faithful, right? So using that, it follows that like this xi f x alpha is an equivalence for affine x alpha. Now we'll use actually okay, so let me write it down. So we'll use this proposition, so like basically base change, I guess. So we've also seen this, by the way. So I'll just recall this real quick. So f from x to y is a morphism of geometric stacks. And for any Cartesian square of geometric stacks, so say x prime to y prime, and this is like, say, g prime. This is g, and this is f, right? The induced square, where I'll just write it down. So this induced square could you call PST comp, and then the arrow goes to this direction. Sorry, this was x. Okay. 2q cop PST comp x goes upwards of upper star 2q cop PST comp y prime. This is g upper star 2q cop PST comp y. So this is like vertically right adjointable, right? So this basically lets us glue these like in a psi f. So let me write it down. This lets us glue these the equivalences psi f x alphas along the check nerve of the cover. It's alpha to x, right? Okay. So let's sketch it, the fully faithfulness real quick. So for fully faithfulness, like, given some, say, I don't know, C and C alge, sorry, yeah, let's maybe let's say it like, oh, okay. So yeah, let's start with this initial switch activity, because that's what I was writing. So given like the C in C alge, C alge 2q car est com xf, right? It's pullback to each x alpha is of the form f star z alpha for some f alpha from z alpha to x alpha, right? Now the base change property ensures these glue to a map z to x with this, since this being called C. Right? And for fully faithfulness, so the fully faithfulness thing, take f and g both from z to x, then this map from fg to psi f g. So yeah, this can be checked affine locally on Z, where it follows from the affine case. Right. So that was the first case. And now the second case is like general case. Okay. So that is X has a quasi-affine diagonal. Okay. So start with this lemma. So this also, I think we have seen this before. If P from U to X is quasi-affine, and Z is affine, then this Q co X, Q co U, Cn should Z Cn. So this is like for some. So we saw an affine version of this quasi-affine scheme set. Right? So yeah, I'll skip the proof sketch of this part. So we'll actually use this lemma, right? So now let's extend this definition. So we had this definition of C algebra of column F mod Q coaxiant. So now let's extend the definition to do this category. So instead of F, we have QF, it's quasi-affine. So so the objects are like C5, where C is just like Q call Z, and where Z is quasi-affine. Right. Now the lemma is psi x, QF x is an equivalence. So let's see a proof sketch. So this actually, so I'll just say that we have the same descent argument as 2. So start 2. Let's go back. And so yeah, this part. So the proof of this lemma. So the kind of descent argument that we used here. So yeah, as this, but right. So now using the previous lemma. So previous lemma as in this one. By using the previous lemma, we can to ensure that the local pieces are quasi-affine. Right. I mean, the key is that for a quasi-affine map, say from U to X, the pullback, roughly speaking, the pullback of an affine algebra object remains quasi-affine algebra object. Okay, lemma. So the inclusion, so this graph comp to CH graph comp QF is an equivalence when restricted to objects coming from maps Z to X, where yeah, with Z is affine. So right, so proof sketch. Let's see proof sketch. So if C is like equivalent to Q cos Z Cn with Z quasi-affine, and the map going Cn to C comes from a map Z to X, then Z is affine. So this is also something that we have seen. This is like Theorem 4.2.2 of Stefanich. No, I don't think we've seen this. So let me state this real quick. So if you call ZCN is equal to mod CNR as Q call X CN algebras, then Z is affine. Right. So that basically proves this part. Therefore, we have shown that this f(x) is also an equivalence. Right. So the last thing that I have to say is like, how do you deduce? How to deduce theorem 4.2.1 now from this? So right. So take fibers of the Cartesian square from so I don't remember what lemma. Oh yeah, it was lemma 3.5.1. Stefanich over y is equals to spec r q call ycn. And the left fiber is yx, and the right fiber is c alg graph comp q cox cn co-ICN. Right. So which is equal to like PRL, basically, like graph comp is in PRL. So yeah, so now since the square is Cartesian and this is an equivalence, so that will imply that these fibers are equal, right? So I'll just write one corollary. So maybe let's say it's an application, so it is a corollary. So right, so from there's a map from with quasi-affine diagonal. So you get this formula x tensor product formula. Oops. Okay, that happened again. So probably I lost what I had before. Yeah. So that was one corollary, and another corollary that I want to say is yeah. I'll just stop there. And once again, I'd like to thank everyone who had participated and give a talk. And yeah, that'll be it. That'll be the end. And now, yeah, I'd be open to questions. If not, we'll move to post-recording session. So questions. Okay, if there are no questions, I'll stop the recording and go to the post-recording session.